Now in this video, I'll just introduce the idea of displacement current, an extension or modification of Ampere's law. You're used to things in more recently, magnetism and potential and different ideas being quite abstract in electromagnetic theory, so this is another case in point. And hopefully it will seem reasonable to you nevertheless, and it is kind of a foundational thought for Maxwell's equations, so kind of an important idea. Now, conduction current, we'll call that IC, C for conduction. So we have capacitor plates, and we know that when we have current flowing, call it this conduction current, actual flow of charge on a wire, that charge builds up on the plate, pushes charge off the other plate, and we have conduction current on the other side of equal value. Now we can take a region and encircle it and discover that there is a magnetic field produced by this current. Right-hand rule, up here it comes out, down here it goes in. And the same thing is going to be true over on the other side as well. Same situation. Now that's a magnetic field that we can measure and verify that it exists at those locations. And the closed integral, the closed line integral of B dot dl is mu 0 I enclosed being the conduction current, so we have mu 0 IC over 2 pi r. That is the actual size of the B field in Tesla. All right. Now, what about what's going on over here? Is there a conduction current between the plates? Or is this just a line of demarcation in the universe? And different laws of nature apply here. Well, not really. So do we have conduction current? Closed integral of B dot dl now is mu 0 I enclosed. But what's I enclosed? There's no charges floating across there, are there? So that would seem to be 0. There is no actual current enclosed. So we should expect the B field to be 0, yes? Well, maybe. B is 0 here is what the conclusion would be, but do we expect the B field to be continuous up to this point? Just immediately stop and then pick up again here. There's reasons to assume that that might be fallacious reasoning. Well, as charge accumulates on the plates, the electric field between the plates does something. It starts going up. And so the following relationships will hold for this situation where the charge is capacitance times voltage. Well, that's epsilon 0 A over D, the geometric expression for the capacitance. Voltage, we got an electric field times a distance. So that's ED, so that simplifies. So Q is epsilon 0 AE. But what's AE? Area times electric field is electric flux. So that's epsilon 0 phi sub E. So we have an electric flux times epsilon 0. Well, conduction current is dq dt. So if you consider Q here and take the time derivative of it, we get epsilon 0 d phi sub E dt. Well, now what we're going to do, little trick, may seem a little gratuitous to you, but hang in there. Let's invent a fictitious current and call it displacement current. Yeah. The displacement current is defined to be consistent with the conduction current, because we have something passing through here, right? We have conduction current, nothingness, the nothing. And then conduction current again. No, there's something going on there. So that from this side to this side, it doesn't look like anything has changed. You got a black box. Here's a black box. You put current in, you get current out. What's going in the black box? You might just assume it's just a wire. How could you tell the difference? You would think that nature would act in such a way as to do something to basically replicate the scenario of a wire passing through in the black box situation. So we're going to invent displacement current and call it epsilon 0 d phi sub E dt. It's like what we got here to be consistent with it. And what's nice is we can relate in a practical sense a changing electric flux in this region of space, because we have in that region of space an electric field. And not only that, but that electric field is changing, rising or falling. And that changing electric field then gives rise to the displacement current. So there you go. Here's some validation. So here we're going to call it ID for displacement current. Closed integral of B dot dl equals mu 0 I conduction plus I displacement. So this is the modified form of Ampere's law. It includes regular conduction current and displacement current that we just defined. But now, I guess still the question remains, is there any physical, empirical validation for the reality of this displacement current so that Ampere's law doesn't apply to just regions where there's an actual flow of charge, but in addition, a changing electric flux, or an increasing or decreasing electric field? Well, let's consider that. So let's test this Maxwellian idea and see if there's any validity to it. Nothing like seeing what nature actually tells us, is there? So here we have the geometry again. Here's the electric field. And here's a region within this total electric field area compared to the entire area. The outer line here, the outer circle, encompasses all of it. So I enclosed by a circle of radius r the current density, the displacement current density times the area is the displacement current. Then modified by the ratios of the areas to get how much is enclosed by the region of radius r. So pi little r squared over pi big R squared equals I displacement r squared over r squared. That's I enclosed. Now, closing integral of B dot dl, b 2 pi r, that is the integral, the line integral. Mu 0 I enclosed, which is mu 0 I dr squared over r squared. So what's b? Well, just divide that last expression by 2 pi r. And then one of the r's goes away. Mu 0 I dr over 2 pi r squared, which is also, looks very similar to what we got, mu 0 r over 2 pi r squared IC, conduction current, for a solid conducting cylinder of uniform current density. So that's pretty interesting. I guess the last thing that we might want to consider then is if we put a magnetic field sensor in the region of space at location R, what do we discover? Is it there? Yes, it is. It's there. And not only is it there, but it matches the theoretical value we derived. Which really what that does is establishes the reality that a changing electric field produces a time-varying magnetic field as well. And that statement is at the heart and soul of electromagnetic theory that will all come together, be synthesized by Maxwell, and we will progress at least just ankle deep perhaps in the development of that theory.